All right, what's going on, y'all? Well, before I get started on the problem, I just realized I got 111 subscribers. I had no idea. I haven't checked this thing in a cool minute, but that's pretty cool. You know, I'm guessing now that school's starting, there's going to be a lot more views. But, I mean, just to give you guys a little background, the reason I started this channel was for my little sister that she's gonna become a ME student soon, and I want to kind of make these videos right now that this kind of stuff is still fresh in my head, if that makes sense. So, I mean, I didn't realize I was helping so many other people. I've kind of been checking the comments, people saying, good work, man, that feels cool, you know. But you know what, that's enough. Let's go ahead and get started on this problem. It says, analyze the space truss. It's composed of 4 nodes. Their coordinates are in inches, and there's 3 elements. They give us the cross-sectional areas. They give us the modulus of elasticity. There's a force of 1,000 pounds at node 1 in the negative z direction, and nodes 2 through 4 are supported by ball and socket joints. So hit up statics if you want a refresher on that. But okay, so prevents movement in the x, y, and z directions. Node 1 is constrained from movement in the y direction, so that's cool. They give us 10 boundary conditions, so that's going to make this problem a whole lot easier. But you know what, let's go ahead and get started. It doesn't tell you what to find, so we're going to go ahead and find displacements and stresses in each element, and that should be enough. So let's go ahead and get started. All right, so there's a lot going on in the paper, but just follow what I say. We'll cover everything. The first step here is we want to find EAL, right? Because we know this is the formula for 3D stiffness matrices and all that good stuff, right? What we're doing right now. It's between 2 nodes, right? In this case, node 1 and node 2. And it's this big 6x6 matrix. And it's symmetrical, you know. I think the book calls this little 3x3 a lambda. That's all it is, right? It's a positive lambda. And here they turn negative. Here they're negative. Here they're positive. Just divided into 4 quadrants. And that's all it is. But the reason I'm bringing this up, right? We want to find L for every single bar. So we really can't start doing the problem until we know the lengths. Sometimes they give it to you. In this case, they don't. But this is the distance formula for 3D. If you remember from calculus, I think it was. Damn, that was a long time ago. But it's just a change in x, change in y, and change in z. Final minus initial, right? I like to have in this case, right, my initial is going to be at node 1. I like to go from the small node to the big node. So for element 1, we're going to go from 1 to 2. For element 2, we're going to go from 1 to 3. And then from element 3, we're going to go from 1 to 4. And that's really all it is, right? So let's go ahead and do the length 1 for this one. So it's the final coordinates minus the initial coordinates. So it's 0 minus 72 for the x. So that's going to be negative 72 squared plus change in y, 36 minus 0, 36 squared, right? Plus 0 minus 0, that's just 0 squared. If you do the math, you will get 80.5 inches. This is in inches, right? It tells you here. Truss is composed of 4 nodes whose coordinates in inches are shown, whatever. Yeah, so we do the second one now. So it's 0 minus 72. That's negative 72 squared plus, now it's 36 minus 0. So that's 36 again. And then 72 minus 0. 72 squared. If you do the math here, you will get 108 inches. And finally, if you do the math here, so it's 0 minus 72, that's negative 72 squared. 0 minus 0 plus 0 squared. Negative 48 minus 0, that is negative 48 squared. You might not be able to read it, but just follow what I'm saying. If you get the length, if you do the math, you'll get 86.53 inches. And cool, so we got the lengths. We're going to use those lengths to get the stiffness values, right? And we're going to go ahead and get E over L because it doesn't say for some reason, like it doesn't tell you what to find in the problem, but we're just going to go ahead and find displacements at node 1 because that's usually what they ask for. These are fixed, so they're not going to ask for that. And then the stresses in each element. So it's a pretty long problem in the sense that there's a lot of writing, but it's pretty easy. It's just a process. So we got the lengths. We could go ahead and get EA over L now, They give us the A's for each one. For element 1, it's 0.302, element 2 right here, and element 3 right here. They give us E, right, for every single bar is the same. What else? And then L, we just found them. So if you go ahead and do EA over L for element 1, so it's going to be 1.2 times 10 to the 6 times 0.302 divided by 80.5. For element 1, you will get 4.5 times 10 to the 3. That's in pound over inch, okay? We want to be consistent. They might give us feet sometimes. They might give us kilopounds. Just make sure it's pound and inch. Try to keep it just pound and inch. It's going to save your life. Just always keep it the most simple. You can Newton meters, pound, inch, and that's it, right? Okay, do it for element 2 now. So it's 1.2 times 10 to the 6 times the area, 0.729, divided by 108. That's going to give you 8.1 times 10 to the 3. I modified it, okay? It was 10 to the 6, but you get a really small number. Just move the decimal over 3 times. You'll get 8.1 times 10 to the 3rd for all of them, okay? And then do the same thing for the third one, 1.2 times 10 to the 6 times 0.187 divided by 86.53. You will get 2.6 times 10 to the 3rd. And then I didn't do it for the other ones for E over L, so let's go ahead and do that. 1.2 divided by 80.5 in this case. That's some number times 10 to the 6. So we're going to alter that number. I'm going to put 14.9 times 10 to the 3rd. Okay? Double check the math, but it's right. I already did the problem. What else? 1.2 divided by 108. That's going to be 11.1 times 10 to the 3rd. And finally, 1.2 divided by 86.53. That's going to be 13.87 times 10 to the 3rd. And I'm confident in these numbers because they sound familiar. I just did the problem again, right? So this was step 1, right? Lengths. Let's go ahead and mark this as step 2. Now we're on step 3, direction of cosines. I'll explain this in a bit, okay, just FYI. But direction of cosines. So if you remember from 2D, you use the angle itself. The angle of the beam relative to the node, all that good stuff, right? Watch the other videos if you're confused. But now it's pretty much the same thing. Now we're just using, so you know how cosine is adjacent over hypotenuse, right? Trigonometry, that's all it is. So it's the cosine of the angle is equal to adjacent over hypotenuse. And that's what this is pretty much telling you for each bar. That is the direction of the cosine. Now there's theory to that. I'm not going to go into it, but that's kind of what's going on if you're curious. So let's go ahead and start filling in this table. So the reason I make this table, right, you're going to need CX, CY, and CZ, obviously direction of cosines, to get the squared values. And then the reason these values come up is because from your matrix, right? We got all these. We got to fill in this matrix for each element. And CX, CY, CX squared, CY squared, CZ squareds. And the rest are just a combination of all of them. But that's why we need to do this. You're also going to need these 3 when you're finding stresses. But when we get there, I'll explain that. Yeah, we could go ahead and just continue to bring the problem, right? So what this means, damn, I'm going a little fast. My bad. Final minus initial. Okay, so we're gonna do it for each element. Let's just stick with 1 for now. It's the final minus initial of the x coordinate, and that's all it is, divided by the length of the beam. In this case, it's 80.5. Okay. Yeah. So if we do that, we'll get for the first element 0 and 72, right? So it's gonna be 0 minus 72 divided by 80.5. If you do that math, you will get negative 0.894. For CY now, it's 36, and it's the final, okay? Remember, this, you don't use 0 minus 36. You do 36 minus 0 because this is our final position. This element is going from 1 to 2. So that means 2's your final, 1's your initial. So 36 minus 0 divided by 80.5, your length. If you do that math, you will get 0.447. Finally, 0 minus 0 over L, that's just 0. And cool, we got the 3. Now, before I continue, I'm gonna go ahead and fill out the rest of the table. If you square cx, you're gonna get 0.8. If you square cy, you're gonna get 0.2. Square cz, that's 0. Anything that has a cz is 0, so those two are 0. Then multiply cx times cy, these two, you're gonna get negative 0.4. All right, now we just do that for every single element. Now we got element 2. That one's going from 1 to 3. Node 1 to 3, right? And same thing. So xf minus xi, 0 minus 72, it's negative 72 divided by 108 now, because we're on element 2. That's going to be negative 0.667. If you do the y's now, 36 minus 0, that's 36 minus 0 divided by 108. That's going to give you 0.333. If you do the next one, 72 minus 0 divided by 108 now, right? Element 2, don't forget. That is positive 0.667. Fill in the rest of the table, cx squared. When you square it, you're going to get 0.444. When you square cy, you'll get 0.11. When you square cz, you'll get 0.44. And then do cx cy, that's going to be negative 0.222. cy times cz, that's going to be positive 22, right? 0.222. Then cx cz, it's negative 0.444. Finally, last one, right? Now we're focused on these two positions, final minus initial. This one goes from 1 to 4, so we're starting at 4, going to 1 to subtract 0 minus 72, it's negative 72 divided by 86.53. That is negative 0.832. Do the y's, 0 minus 0, that is 0. Doesn't matter if you divide, right? It's 0. Negative 48 minus 0, that's negative 48 divided by 86.53. That is negative 0.555. And we start filling up the remaining part of the table. So cx squared, that's going to give you 0.692. cy squared is 0. cz squared is 0.308. cx cy is 0. cy cz is 0. And 0.462 for cx cz. Now, we will go ahead and that was step 4 right here. We're going to step 5. Now we're gonna start assembling the little matrices. I forgot the name of it, right? But the little matrix per element, so later we could get the global stiffness matrix. So let's go ahead and do that, right? K1 for element 1, the stiffness, we're following this formula, okay? Damn, keep forgetting. We're following this formula. It's K1 is equal to EAL of that element, and then between whatever nodes it's in, and then just fill in the values. That's all we're doing. So that's the formula right there if you want to screenshot it or whatever. And then I'm gonna remove it, just FYI. But the element stiffness for element 1, it's 4.5 times 10 to the third, EA over L. Now, EA over L, that's just 4,500, right? 1, 2, 3, yeah, it's 4,500. So we're gonna put 4,500, okay? It's the same thing. And this one is between nodes 1 and 2, element 1. So it's going to be U1, V1, W1, U2, V2, W2. Same thing going across, U1, V1, W1, U2, V2, W2. Now, it's like, okay, so look, I didn't really explain it at first, but I'm going to do it right now. It's real important that you stay consistent with the direction of the nodes, okay? In this case, look, they even gave us a little arrows, but it doesn't matter. You should know how to do it. So if you would have went from 2 to 1, these would have been your final position. Let's say, right, if you went from 2 to 1 instead from 1 to 2, this would have been your final position. This would have been your initial. So some of these signs might have, they would have changed. Everything's going to change now. It's not going to affect you when you make these little matrices and overall your big matrix. But when you get to the stresses in each element or forces in each element, it's going to ruin your signs. It's too much to explain, but just point is, be consistent. So if you went from 1 to 2 like we did, we're gonna go U1 V1 W1, U2 V2 W2. If you would have went from 2 to 1, you would have had U2 V2 W2, U1 V1 W1. They would have just switched. But just, you gotta understand that that's really important, okay? So cool, we'll keep that for now. Hold on, I don't wanna fill it in just yet. For K2, our stiffness is 8100. So we're gonna put 8100, and that goes from 1 to 3. So it's gonna be U1 V1 W1, U3 V3 W3. Fill it in this way, U1 V1 W1, U3 V3 W3, okay? And finally for K3, your stiffness is 2600 now. So we're gonna put 2600, and that goes from 1 to 4. So it's gonna be U1 V1 W1, U4 V4 W4. Same thing going across, so it's U1 V1 W1, U4 V4 W4. And yeah, so before I start filling them in, I'm gonna get to this now. So they told us nodes 2 and 4 are supported by ball and socket joints. And if you remember from statics, that just means there's a Fx, Fy, and Fz reaction. Because they don't move in the X, Y, or Z, it's just like a ball, like a shoulder. You know your shoulder? You can move up, down, left, right, and the other direction, whatever it is, right? But you can't, and you got moments, you know, you don't have any moment reactions because you can move them. That's all it is, right? That's just saying that U2, V2, all these, they're fixed. So you can't move them up and down, left or right, whatever, in any of the 3 directions. But how can I say this? There's the moment. Sorry, I'm getting a little sidetracked. But point is, you have those 3 reactions, okay? And it can't move in those directions. So you have these boundary conditions. U2, V2, W2, 3, and 4, they're all 0. So that's gonna make our problem a whole lot easier. And there's one more thing. They also said roller preventing Y displacement. So that means at node 1, the V direction or the Y direction is also 0. So we have these 10 boundary conditions. So it's actually making our problem really, really easy because they just cancel out. So U2 is 0, V2 is 0, and W2 is 0. Okay, so I'm gonna do that. Right, boom, all these are gone. Okay, now the same is the case for node 3. That means these are gone. Hopefully I didn't confuse you guys with that ball and socket, whatever. But if you're confused, just YouTube it. Statics, I forgot how to explain it, I'll be honest. But and then node 4, same thing for node 4, okay? But yeah, just if you were confused, just check it out so you can see what I mean. But point is, displacement is 0 in all 3 directions. And then finally, I applied all these 9 boundary conditions right here, right? That's what you just saw. Now we need V1. V1 is also 0. Boom. And the reason I like doing this first is, look, it saved us a ton of writing. I was supposed to plug in every single number for each one, right? But now I only got to worry about 4 slots in each of the matrix. And it's just this one, this one, this one, and this one for all 4. For all 3, I mean. So look, this is what we're going to do. I'll pull up the thing again. Okay, so this, right here, let me do it like this. So you see how this is for each element. This is the stiffness matrix for each element. That's what we have here, right? It's a 6 by 6, right? 6 by 6. And we would have normally filled every single position. What this symmetrical means that is this goes here, this goes here, this goes here. Same thing for all 4 of them. Just be careful with the signs, right? But because we applied the boundary conditions, we don't worry about, because let's just focus here. So these last 3 columns are gone. So all these 3 are gone. We don't care about them. All this is gone, the last 3 rows. This one's also gone, V1, right? Remember? And then V1 is gone this way. So we only care about CX squared, which is going to go here, CZ squared, which is going to go here, CXCZ, which is going to go here, and then symmetrical, so CXCZ, which is going to go here. And we're going to go ahead and fill that in just like that. So for the first element, CX is negative 0.894, CZ is 0, CXCZ is 0, and CXCZ is 0. So that one's done. Let's go to the next one, element 2 now. We got CX, which is negative 0.667. We got CZ. Oh, actually, hold on. My bad. I messed up. Give me 1 second. We use the squared values, not the what do you call it? Not the normal values, the squared. So it's actually 0.8 here, okay? Whew, glad I caught it. Here, we're gonna have 0.444, right? CX squared for element 2. CZ squared was also 0.444. CXCZ is negative 0.444, whatever. Okay, so we got that. Yeah, that one's correct. Thank God I caught it. Okay. Next one, finally the last one. We're gonna have CX squared 0.692. CZ squared, which is 0.308. Again, I'm just following the formula I showed you on the other piece of paper. Nothing crazy. CX, CZ. We only cared about these columns, okay? Just FYI. If it makes it easier for you. 0.462, 0.462. All right, cool. Now, we cannot add the matrices just yet, right? To make the big global stiffness matrix, like we've been doing in other chapters. We cannot do it because they don't share the same stiffness value outside the matrix. So it's easy to fix, right? Just multiply 4,500 to all of these, multiply 8,100 to all of these, multiply 2,600 to all of these, and that's gonna give you the ability to add them later. So let me go ahead and do that. All right, so I went ahead and did that, right? So I multiplied 4,500 into everything, same thing here, same thing here. Now what we could do is, well, what we have to do actually is erase the outside one. All right, so that's out. 8,100 is out. I don't have the best eraser. 2,600 is gone. And we're good. So now that they have nothing outside, right, we could just add them. So we're gonna add all the U1s together, all the, well, U1 U1s, the U1 W1s, and just pretty much, I hope you know what I'm saying, right? 3,600 plus 1,800 plus this, 0 plus 1,201 plus that, 0 plus that plus 1,201, 0 plus that plus 800. And that's it. So I'm gonna go ahead and flip the page, and this is your global stiffness matrix, okay? So remember, we canceled just the way we did here, apply the boundary conditions. We're gonna go ahead and do that here as well. So let me go ahead and do that. I'm just gonna cancel V1 and everything from U2 forward because they're all 0. And same thing here, V1 and U2 all the way down. All right, so I did just that, right? Excuse the lines, are not the best, but if you add all the U1 U1s, remember, you get 9,000 up here. And I did some rounding on the other numbers. It shouldn't mess us up. It's not that big of a deal, but these are the numbers you get if you do the math. And that means we could go ahead and start pretty much solving the equations, right? We have 2 more boundary conditions. Hold on. Now look, it says roller preventing Y displacement. That means if it's preventing displacement, that means there's a force acting on it. So we don't, normally we would have put, it tells you here, right? 1,000 pounds, node 1, negative Z. So that means F of Z is negative 1,000. And just by looking at the schematic, force of X is 0. And normally it would have been Y of 0, but they told us it's preventing displacement. So that means there's a reaction force at Y. Now, if you've been watching the other videos, I've told you, you either know displacement at a node or the force at a node, but you never know both, in FEA at least, okay? Well, I mean, the first class too. I don't know about the advanced. I think advanced is just doing software and all that good stuff. But just remember that you either know displacement or you know force, but you do not know both. So in this case, we know the force at 1, it's 0. And at z, it's negative 1,000. Okay, so it's 0, negative 1,000. And we know displacement at every other one. Displacement v1 is 0, and then remember we applied all these boundary conditions. All these were 0. So you knew displacements, you didn't know force. And here we know the two forces, but we don't know displacements, u1 and w1. And that's what we're looking for. And technically, once we find them, you could find forces, but that's going to be a huge headache. Get a calculator, because your professor's not going to make you do it. But if he does, then just know I'm praying for you, right? So this is step 5. This was step 6. Let's go to step 7. Doing the equation. So it's 0, right? This 0 is equal to 9,000 u1 minus 2,400 w1. Then next one is negative 1,000 is equal to, right, negative 2,400 u1 plus 4,396 w1. All right, so this is what we're gonna do. We're gonna go ahead and multiply the top equation. We're just solving for unknowns, nothing crazy. Should have done this back in high school, I think. So I'm gonna go ahead and get rid of u1. You can get rid of this one too, it doesn't matter which one. So since this is a positive, this is a negative, that means these two, whatever I multiply them with, should be the same sign. And so the top is 2,400 and the bottom is 9,000. Just swap them. That's all I did. And if you do that, your new equations, what are you gonna get? You're gonna get 0 is equal to, do the math right, 9,000 times 2,400. That's gonna be 216, 1, 2, 3, 4, 5 zeros. u1 minus 2,400 squared, which is 576, 1, 2, 3, 4 zeros. And then 9,000 times negative 1,000, that is negative 9 million, I think it is, right? 1, 2, 3. Negative 2,400 times 9,000, you get negative 216, 1, 2, 3, 4, 5 u1. So that's good. They're gonna cancel out. And plus 395,640,000. This number times that number, it's that number. Okay, so if you add them, you will get this canceled out. Okay, so it's negative 9, 1, 2, 3, 4, 5, 6 equals 33804,123 w1. So that means w1 is negative 0.266 inches. That's your answer. Then w1, plug it into any of these two equations. u1, you will get negative 0.0709 inches. Those are your displacements. All right, and it kind of makes sense, right? If you're pulling down, I don't know, you really can't see the x, right? But actually you can, because you're kind of pulling it and it's kind of wanting to go around the node, right? So x is negative displacement, so it's gonna end up somewhere here. Then obviously you're pulling down, so your z displacement is gonna be negative too. So yeah, these numbers make sense. Now let's go ahead and do the stresses in each element. So we got that. The formula for that is this. It's E over L times, and this is where, you remember I told you, be consistent with whatever direction you're going with each node, at each node. I mean at each bar, you know, from node 1 to 2 in our case, 1 to 3, 1 to 4. If you would have chose the other way, actually if you would have chose that way and then but you messed up your matrices here, remember you would have put U2, V2, W2, U1, V1, W1. That would have messed with these signs. So that's what I'm saying, always be consistent. If your professor only asked for the global stiffness matrix for the problem, then yeah, fortunately that's not gonna mess you up. But once you go past the global stiffness matrix, this is where it's gonna mess you up. So let's do that, right? We got, what are we doing? Stresses, oh, stresses, that's right. So for sigma 1, it was E over L. Remember, we got 14.9 times 10 to the third. Okay. And that formula I showed you, it's negative CX, negative CY, negative CZ. So if you do that, CX, CY, CZ, just change their signs for the first set. That's going to be 0.894, negative 0.447, and 0. And then just switch the signs to the original ones, 894, positive 0.447, and 0. Okay, now this is going to get multiplied to the displacement vector. It's U1, V1, W1, U2, V2, W2 for element 1, because it's between nodes 1 and 2, right? So it's U1, which was, we found, negative 0.0709. V1 was 0, right? Remember the boundary condition? Then W1 was 0.266. Then U2, V2, W2 were all zeros, boundary conditions. So that's how it's going to look for all of them, actually, because they all start at node 1. So your first three are U1, V1, W1. And then U2 to W4, remember those 9 boundary conditions, they were all 0. So these 3 will always be 0, because it's going to be node 2, then node 3, and then node 4. Just FYI. But do the math, right? Sigma 1, you will get 14.9 times 10 to the third. This number times this number, plus this number times 0, plus 0 times this number, plus this number times 0, plus this number times 0, plus this number times 0. So we only care about the first one, actually, because everything's 0. So if you do that, you will get negative 0.0634. And then that means sigma 1 will be negative 945 psi. And that negative means it's in compression. Okay. Do the same thing for element 2 now. That E over L value, what was it? 11.1 times 10 to the third. So let's see. 11.1 times 10 to the third. CX, CY, and CZ, but the first ones are negative, so switch the signs. Trust me on this, I'm not going to flip the paper, but it's 0.6667, negative 0.333, then negative 0.667, sign switch, 0.667, positive 0.333, positive 0.667. And same thing, right? Negative 0.0709, 0, negative 0.266, 0, 0, 0. All right, now do that math. Sigma 2 is equal to 11.1 times 10 to the third. This number times this, plus this 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 times this. All right, I forgot the bracket. Okay, that means we only care about this one and this one, because, right, the rest are 0. You will get negative 0.0473 plus 0.1773. Do the math. You will get sigma 2 is equal to 1443 psi. That is positive, so it's in tension. Let's box that up. Finally, sigma 3. What was the E over L? 13.87 times 10 to the third. 13.87 times 10 to the third. Bracket negative CX, which is 0.832. Negative CY, which is 0. Negative CZ, which is 0.55. Now in the sign switch, back to your original. So it's negative 0.832. Negative 0, whatever, and then negative 0.555. Bracket, that is negative 0.0709, right, from 1 to 4 now, the nodes. Okay, we got 0, negative 0.266, 0, 0, 0. And yeah, do the math again. Sigma 3 is equal to 13.87 times 10 to the 3. Now this times that, this times that, this times that, everything, right? So we only care about the first, this one, and this one, these two. So you will get negative 0.059 minus 0.1476. Finally, sigma 3 is equal to negative 2865 psi, and that is in compression. And yeah, that is the problem. Finally, we got the stresses. Damn, these problems are long. But you could kind of verify these stresses. Sometimes, in this case, let's go ahead and see. It's saying sigma 2 is in tension, so it means element 2 is in tension. And yeah, it makes sense. If you're pulling it down, that means you're stretching this one. So that makes sense. You really can't see how these two are in compression. Well, you kind of can, right? If you got negative displacements, that means you're pushing into this node, right? Going into node 2. Into node 4, I really don't see it, but trust your gut, you'll be all right. But that's kind of the process, right? You want EAL, so you usually have to find lengths. Then once you have your lengths, you find EAL. In this case, you can find E over L right away, just to have it ready. Then you go to direction of cosines. You want to get all these values for each element, and then get the squared values and then these values to make the big stiffness matrix. Eventually, right? First, you got to make the little matrices for each element. And that's kind of where you use these values. Now you can't add them yet until you have the same value outside on each. In this case, there's nothing, right? So that means we could add them. Then after that, you just solve for your unknowns, no big deal, boom, boom, boom. In this case, a lot of things got canceled out because of the boundary conditions. Again, do the boundary conditions before you start filling this stuff in, because it's gonna save you a lot of time. And yeah, that's pretty much the problem. Stresses in each element, boom, ready to go.